Imagine you have this friend, like an absolute savant.
Yeah.
They can recite the entire encyclopedia from memory, right? They can compose a flawless Shakespearean sonnet on the spot and translate complex physics into 5 different languages.
Sounds like a pretty intense friend.
Right. But if you ask this exact same friend to walk into a brand new kitchen and just make a simple cup of coffee, they somehow manage to set the microwave on fire.
Yeah, and that highlights a really severe limitation. Knowing the text associated with the word fire and understanding the actual physical consequences of, interacting with a fire, those are 2 entirely different cognitive processes.
Exactly. That disconnect is the core issue here. And that image, the brilliant savant who is completely helpless in a physical or simulated space, that is actually the perfect lens for looking at the current state of artificial intelligence.
It really is spot on.
And that's why we're doing this deep dive today. You sent us this fascinating paper titled AGEL-Comp, a neuro-symbolic framework for compositional generalization in interactive agents.
Yes, authored by Manur Shahid and Hannes Roth.
Right. And for you listening, if you're here because you want to understand how researchers are trying to push AI past just, generating text into truly interactive, grounded systems, you are in exactly the right place. This paper completely reframes the conversation.
It really does. We are at a critical bottleneck in the field right now.
Yeah.
The paper tackles what researchers call the compositionality crisis.
The compositionality crisis.
Yeah. And they're addressing it by taking the generative brains of large language models and, constraining them with the strict, rigid logic of traditional symbolic AI.
Okay, let's pull that apart, because before we get to this neuro-symbolic hybrid thing, we need to define the actual bottleneck. What exactly makes this a crisis?
Well, the underlying mechanism of an LLM is essentially statistical pattern matching.
Right, predicting the next word.
Exactly. They predict what comes next based on just vast amounts of ingested data. And this makes them highly fluent, obviously. But they struggle severely with what we call compositional generalization.
Which is what exactly?
In cognitive science, compositional generalization is the ability to take known, primitive concepts and understand entirely novel combinations of them systematically.
Okay, I think I follow, but give me a tangible example of that.
Sure. Think about human reasoning, right?
Hmm.
If you grasp the concept of grab and the concept of an apple and the concept of boiling water,
Okay.
you can instantly understand what it means to grab an apple out of boiling water.
Right, yeah. I don't want to do that.
Exactly. You don't need to have witnessed that specific event thousands of times to predict the outcome. You systematically combine those primitive concepts and immediately deduce that, hey, I'm going to get burned.
So you basically build a causal map of the situation on the fly in your head.
Precisely. And the paper argues that current LLMs completely fail at this in interactive environments.
Why, though? They know what boiling water is.
They fail because their knowledge is fundamentally disembodied. It's completely detached from a structured physical reality.
Oh, I see.
When an LLM encounters a novel combination of elements in a simulated space, its statistical guessing engine tries to find a text-based pattern rather than actually reasoning through the physical constraints of the scene.
It goes right back to that student who memorized the entire cookbook without ever stepping foot inside a real kitchen.
That's the perfect analogy.
They have all the vocabulary of cooking, but you put them in front of a real stove, and they just don't understand the physical consequences of their actions. They just know which words are statistically likely to follow the word stove.
Exactly. And the researchers recognize that simply scaling up neural networks, throwing more data or compute at the problem, that doesn't cure this disembodiment.
A bigger LLM just becomes a more articulate guesser.
Exactly. So to actually solve the crisis, they had to design a completely new architecture that actively forces the AI to learn the structural rules of its environment.
And that architecture is AGEL-Comp, which stands for Action-Grounded Experiential Learning for Compositionality.
Yes, quite a mouthful.
It is. And the testing ground they built to evaluate it is this custom 2D action RPG simulation called RetroQuest.
Right.
I looked at the images in the paper. It looks exactly like a classic pixel art video game, complete with goblins, shiny coins, fires, pumpkins, and a standard, health point system.
Yeah, RetroQuest serves as a highly controlled laboratory for testing this kind of compositional logic. And the AGEL-Comp framework, deployed inside it, operates on what they call a neuro-symbolic architecture.
Okay, so we are essentially mashing up 2 completely different eras of computer science here. We've got modern neural networks on one side and old-school symbolic logic on the other.
That's exactly what's happening.
So how does the architecture actually structure that?
Well, it breaks down into 3 distinct interdependent modules. The first is the LLM core. You can think of this as the planner.
Okay, the planner.
Right. It receives a goal in the environment and uses its generative flexibility to propose candidate actions.
So it's basically the brainstormer throwing out ideas.
Exactly. Now, the second module is the causal program graph, or CPG. This is the agent's world model.
The world model, got it.
Functionally, it is a modular directed hypergraph. It stores all the explicit procedural and causal knowledge the agent has about the world.
Okay, wait, let's pause on directed hypergraph. What does that actually look like for the AI?
Sure. So in a standard graph, a simple line connects point A to point B, like fire connects to burn.
Simple enough.
But in a hypergraph, a single connection, an edge, encompass multiple nodes simultaneously.
Oh, wow. Okay.
This is crucial for causal logic because real-world consequences almost always require multiple conditions to be met at the exact same time. The rule isn't just fire equals damage.
Right, because just looking at a fire doesn't hurt you.
Exactly. The hypergraph can structure a rule that says if the agent is near the fire and the agent takes the action to touch, then the result is damage. It allows for highly complex, multi-conditional mapping of the environment.
So we can actually see the rules it's writing. Like, it's not just a web of hidden weights. It's an explicit map of if this, then that.
Yes, absolutely. And we will get into why that transparency is so vital later on. But let's look at the third module first. That's the Neural Theorem Prover, or NTP.
And what does that do?
This acts as the verifier. Before the agent executes any plan generated by the LLM planner, the NTP runs a rigorous mathematical check of that plan against the rules stored in the causal program graph.
Just to make sure it's safe.
Exactly.
Yeah.
It ensures the plan is logically consistent and safe based on everything it knows.
I see the dynamic here. The LLM is like a highly creative but completely reckless driver saying, hey, let's take a shortcut over that cliff to save time.
That's a great way to put it.
And the NTP is the strict collision avoidance system that calculates the trajectory, consults the hypergraph map, realizes it leads to a 500-foot drop, and physically overrides the steering wheel.
Yes. It enforces strict compositional discipline because asking an LLM to self-reflect and check its own work, well, that often just leads to recursive hallucinations.
It just talks itself into a bad idea.
Right. But the NTP provides a provable guarantee of validity based on the agent's current knowledge.
Okay, this sounds great in theory, but there is a massive technical hurdle here. I mean, traditional logic, the kind of the CPG rulebook and the NTP verifier rely on, is discrete.
Yes, very rigid.
Right, a statement is either true or false, a 1 or a 0. But neural networks, the LLMs generating the plans, they're continuous. They're fuzzy, probabilistic systems operating on dense vectors.
That's the core challenge.
So how do you bolt a discrete logic engine onto a continuous probability engine without the whole thing crashing? They don't even speak the same language.
That integration is honestly the most impressive engineering feat in the entire framework. They solve the translation problem by using a shared, trainable embedding space.
What does that mean in practice?
It means every discrete symbol in the rulebook, whether it's an object like a coin or a concept like harmful, is mapped to a continuous vector representation.
Meaning they turn the rigid, absolute words into fuzzy mathematical coordinates.
Exactly. And because everything exists in this shared mathematical space, the neural theorem prover doesn't have to look for a rigid, perfect identity match. Instead, it performs what is called differentiable unification.
Unpack differentiable unification for me.
Well, in traditional discrete logic, if the LLM proposes interacting with an apple and the rulebook only has a rule for fruit, the logic gate just fails.
Because an apple is not the exact word fruit.
Right. But with differentiable unification, the NTP calculates the cosine similarity between the vector for apple and the vector for fruit. It recognizes they are mathematically close in concept and computes a soft unification score.
Oh, I love that. It's like a bouncer at a club who, instead of rigorously checking an ID to make sure your name perfectly matches the guest list, kind of checks your general vibe and decides you are close enough to the demographic they want inside.
That's a hilarious but very accurate analogy. That soft matching allows the strict logic to interface seamlessly with the probabilities of the neural network.
Yeah.
And more importantly, because it relies on continuous vectors, the entire system can be trained end-to-end using gradient-based optimization.
It really is elegant. But it brings us to the operational challenge of the whole system. A highly advanced collision avoidance system is completely useless if it doesn't have a map.
This is true.
When this agent is dropped into RetroQuest for the very first time, its causal program graph is completely blank. It doesn't know what a goblin is. It doesn't know fire causes damage.
It's a blank slate.
So how does the agent populate that hypergraph and actually learn from its environment without a human pre-programming all the rules?
This brings us to the perception-action learning loop. This is the mechanism for genuine empirical grounding. The paper actually outlines a specific example of this process in action.
Let's hear it.
Okay, so the agent is in the RetroQuest environment. Its assigned goal is to pick up a shiny coin. However, that coin happens to be situated right next to a crackling fire.
Setting the board, the rulebook is entirely blank.
Right. Because it has no prior knowledge, the LLM proposes the most direct plan.
Right.
Approach fire, grab coin. The NTP, acting as the safety checker, consults the blank rulebook.
And it finds nothing.
Exactly. It finds no rules regarding fire, so it computes the plan as safe and approves it.
It clears the reckless driver to hit the gas.
Yep. The agent's action module executes the command. It approaches a fire and instantly loses 50 health points.
Ouch.
The system records this as a severe prediction error. The outcome in reality completely contradicted what the empty world model predicted.
So the AI essentially touches the hot stove.
Yes.
Yeah.
And this prediction error triggers the learning phase. Now, the agent faces the credit assignment problem. It knows it suffered a negative outcome, but it must isolate the exact cause.
Right. Was it the act of moving? Was it the coin itself? Or was it the fire?
Exactly. To resolve this mathematically, AGEL-Comp executes stage 1 of grounding, which uses an algorithm called minimal contrastive search, or MCS.
Walk me through how the MCS algorithm isolates the variable.
Sure. The agent accesses its episodic memory, which is essentially a chronological buffer of its recent state action pairs. It scans backward, looking for a minimal pair.
What qualifies as a minimal pair?
Specifically, it searches for a historical state where it achieved the same goal, grabbing a coin, but without suffering the prediction error, the HP loss. Once it locates that safe memory, it juxtaposes it against the current painful memory.
Wow. So to solve one of the most complex problems in reinforcement learning, the system essentially plays a highly rigorous mathematical game of spot the difference with its own memories.
That is functionally exactly what it's doing. And the MCS algorithm only proceeds if it discovers a singleton difference, meaning exactly one changing variable between the two states.
Because if there are multiple differences, the causation is just too muddy.
Right. In this scenario, it compares the safe coin grab to the painful coin grab and identifies that the singular difference is the presence of the fire.
It finds the smoking gun.
Yes. So it formulates a highly specific causal hypothesis. This particular fire caused the loss of HP. But obviously, a framework cannot generalize from a singular instance.
Right.
That leads to stage 2 of the grounding process. Abstractive induction via inductive logic programming, or ILP.
Taking the hyperspecific event and turning it into a universal law, how does the ILP engine do that without, hallucinating?
The ILP uses a technique called meta-interpretive learning. It takes a specific hypothesis, this fire hurts, and cross-references it with background knowledge in the embedding space.
Okay.
It looks at the properties of the object. It identifies that the fire belongs to a broader category of objects possessing the property of being harmful. It then induces a general rule. Any object with the property harmful will cause a loss of health points upon proximity.
And then it carves that newly discovered rule permanently into the hypergraph.
Exactly. It explicitly updates the causal program graph. The rulebook is no longer blank regarding fire.
Which means the next time the LLM brainstorms the idea of grabbing a coin next to a fire, the NTP verifier consults the updated hypergraph, flags the new rule, calculates the impending HP loss, and hard rejects the plan before the agent even moves a digital muscle.
You've got it. It forces the LLM to generate an alternative, safe path around the hazard. The agent has demonstrated true compositional learning.
The mechanics of that loop make total sense, but theory and architecture diagrams are cheap in AI.
They are.
The real question is whether bolting this symbolic logic onto an LLM actually outperforms the pure, massive neural networks that are basically dominating the industry right now.
So let's look at the hard data from the RetroQuest trials.
Let's do it. The researchers conducted extensive testing using 4 state-of-the-art multimodal models as the foundational LLM core. They used GPT-4o, Gemini Pro 2.5, Elavi 1.6, and DeepSeek V1.
Okay, the heavy hitters. Right. And they subjected these models to a 10-quest curriculum. specifically engineered to stress test compositional generalization under varied conditions.
So let's look at the bottom line. How did the full AGEL-Comp framework perform?
The complete AGEL-Comp system achieved a 100% quest success rate across all 4 base models. It consistently navigated the complexities of the environment without failure.
I have to pause on that number. A 100% success rate usually makes me highly skeptical.
I understand why.
Is RetroQuest just too simple of a 2D environment to genuinely test the limits of models like GPT-4o?
It seems simple visually, but the compositional complexity scales rapidly. The quests require multi-step planning, resource management, and hazard avoidance with variables that constantly shift. And the proof of its difficulty is really in how the standard baseline LLM agents performed without the AGEL-Comp framework.
Right. The same models, just without the hypergraph rulebook and the verifier. How did they fare?
They experienced a catastrophic degradation in performance. On the quests categorized as hard and very hard, the baseline models hit a 0% success rate.
Wait, 0%?
0. They completely collapsed when the compositional demands exceeded their ability to rely on just statistical pattern matching.
A drop from 100% to 0%. Okay, yeah, that definitely validates the difficulty of the test. What about efficiency? Because generating new text is one thing, but how quickly does it actually learn the rules of the room? I know the paper tracks zero-shot generalization.
Yes, zero-shot generalization measures the agent's ability to deduce the correct, safe plan on its very first attempt without needing to make a mistake and learn from it.
Okay.
AGEL-Comp achieved a 60% first-try success rate. The baseline LLM, operating purely on statistical inference, managed a first-try success rate of just 3.3%.
Whoa.
Yeah. The Neuro-Symbolic framework was roughly 18 times more effective at initial reasoning.
18 times better before taking a single action. That's wild. And when we look at the broader training footprint, the sample efficiency data is just staggering. When powered by Gemini 2.5 Pro, the AGEL-Comp system required an average of only 23 interactions to fully learn the environment dynamics and succeed. But the baseline LLM required over 159 interactions.
That nearly 7x improvement in sample efficiency is a massive operational advantage. The baseline model requires continuous, blind trial and error, whereas AGEL-Comp experiences a single failure, explicitly maps the rule into its hypergraph, and mathematically prevents that specific failure from ever occurring again.
If we extrapolate that 7x efficiency out to the real world, just think about the GPU compute hours, the electricity, the raw financial cost of training a model on billions of parameters just to get it to understand basic physical boundaries.
It's astronomical.
Right. Cutting that training time down by a factor of 7 just by using symbolic logic is a massive paradigm shift.
It truly proves that pure scale is not the most efficient path to grounding in AI.
The paper also features ablation studies, which I always find revealing. They basically took the system apart to prove why each piece is necessary. Let's start by removing the ILP learner. The agent still has the LLM to brainstorm, and it has the strict NTP verifier, but it loses the ability to write new rules from experience.
Removing the ILP engine causes the agent to fail in a manner almost identical to the baseline models.
Really? Even with the verifier?
Yes. This demonstrates a critical principle.
Yep.
A logical verifier is entirely useless if the underlying world model is incomplete. The agent gets trapped repeatedly verifying and executing flawed plans because it has no mechanism to update its rulebook after a failure.
Okay, now let's test the other side. They put the ILP learner back in so it can write rules, but they remove the NTP verifier.
Yeah.
The agent generates plans and executes them without passing them through the safety checker first.
Without the verifier, the agent's zero-shot success rate plummeted from 60% to 22.5%.
That's a huge drop.
The agent retains the ability to learn, but is forced to learn the hard way. It executes a dangerous plan generated by the LLM, suffers the health point damage, logs the negative feedback, and only then updates its rulebook.
Okay, I'm going to push back on the framing here. Learning the hard way, making mistakes, suffering a consequence, and adapting, that is fundamentally how biological intelligence works.
Sure, it is.
A toddler touches a hot stove, gets burned, and learns not to touch it again. Why is learning the hard way framed as a failure condition for the AI in this study?
Because of the ultimate end goal of this research, which is sim-to-real deployment.
Meaning taking it out of the simulation.
Right. We are testing in a digital pixel game right now, but these architectures are designed for embodied agents in the physical world. If that agent is a 4,000-pound autonomous vehicle or an automated surgical robot, you absolutely cannot afford to let it learn the hard way.
Yeah, okay. You can't let the autonomous car drive into oncoming traffic just so the ILP engine can learn that oncoming traffic causes a negative outcome.
Precisely. In real-world deployment, catastrophic failure is unacceptable. The AI must possess the architecture to simulate and mathematically deduce the consequence of an action prior to execution.
Which is why both systems are crucial.
Exactly. This underscores the necessary synergy of deduction and abduction in the AGEL-Comp framework. The agent requires the NTP verifier to safely deduce outcomes, and it requires the ILP learner to abductively repair its world model when its knowledge proves insufficient. Both modules are strictly necessary for safe, efficient operation.
It makes complete sense. If you're building the brains for a physical robot, you need the rigid safety rails just as much as you need the generative engine.
Yes.
And that brings the whole deep dive into focus. The state-of-the-art research is pointing heavily toward the fact that neither pure symbolic logic nor pure neural networks are sufficient on their own to create robust interactive AI. They need each other.
That's the major takeaway.
We absolutely need the neural networks to parse messy, continuous environments and generate creative solutions. But we desperately need the rigid logic to verify those ideas and explicitly build the causal grammar of reality.
The research definitively shows that true interactive intelligence requires explicit structure. Predicting the next statistically likely token is insufficient for navigating a complex environment. The agent must actively construct and consult a causal model of that environment.
And as we unpack the mechanics of that causal model, specifically the hypergraph rulebook, it seeds a final, incredibly provocative thought for you to consider.
Oh, I know where this is going.
Right. For years, the existential dread surrounding deep learning has been the black box problem. We build these massive models with trillions of parameters, and when they make a decision, we just cannot audit their reasoning.
The logic is smeared across a billion fuzzy vectors.
Exactly. But if frameworks like AGEL-Comp force the AI to explicitly write out its learned causal rules into a causal program graph, could this architecture inadvertently solve the black box problem?
It is a profound implication. The causal program graph, by its very nature, is a human-readable structure. It explicitly defines the relationships and rules the agent is operating under.
Imagine the practical application of that. Instead of guessing why a highly advanced medical AI recommended a dangerous surgery, or trying to interpret the hidden weights of a self-driving car that swerved off the road, we could simply open up its rulebook.
We could trace the exact, interpretable, discrete logic it used to make its choice. The why would no longer be a mystery.
It represents a total shift from treating AI as an opaque oracle that requires blind trust to engineering agents whose foundational logic is fully auditable and debuggable by humans.
It's a much safer future for the technology.
It takes us all the way back to the start. Instead of just letting that brilliant savant loose in the kitchen to guess how a microwave works and burn the house down, we are finally handing them a pen and paper.
Right.
We are forcing them to write down a foolproof, logical recipe card. And most importantly, we can read exactly what they wrote. That's our analysis of the source material today. Thanks for exploring the bleeding edge of AI with us.